So we're going to look over the mock exam for B24. So the first question says that if I let V be a vector space and V1 and V2 be subspaces, true or false? If V1 plus V2 is a direct sum, then V1 plus V2 equal the dim of V1 plus the dim V2 equals dim of V. Well, V1 V1 plus V2 is a direct sum. What this means is that V1 intersect V2 equals the set containing the zero vector. That's one condition. Another condition is that for all x in V1 plus V2, there exists a unique V1 in V1 and V2 in V2 such that V or X equals V1 plus V2. Okay. The definition of a direct sum does not require that V1 plus V2 equals V. This is not a part of the definition of a direct sum. So here, just because V1 and V2 is a direct sum, it doesn't mean that it sums to the vector space. Whatever W is, if I have W equals dim or V1 plus V2, that then dim V1 plus dim V2 equals dim W. But at no point here have I told you that V1 plus V2 equals V. So this is false. Because it's not always true. In our next statement, we have a set of linear transformations. And we have T go in the set from V to W. Provide a condition which T cannot be onto. Here, what I like to do is I like to draw a collection of dots. And for it not to be onto, I have to somehow make the dot so that I can't get every dot. You might also look at this as surjective, not surjective. And here, I look at it and I go, I need more dots in W than I have in V, or more of the dimension of W is greater than the dimension of V. Now, there's many other conditions. You can look at rows, you can look at them being equal and not one-to-one. Now, let's look at question 3. So in question 3, we are given a linear transformation T1 to T2, and we are given a basis alpha and basis beta. We're asked to compute T alpha 1 of beta. So what I want to do is I want to see what T alpha 1 equals. This equals T of 3, 2, which equals 2 times 3 plus 2, 2. And this equals 8, 2. Now that I have it equaling 8, 2, and I have this alpha 1 E2, what I need to do is I need to make the second term match using alpha 1. Because the alpha 1's the only one that has 2's, and then I make up the difference using E1. So this is going to equal 3, 2, and one of those, because that's what makes the second term match. plus some multiple of 1, 0, which is going to be 5. So this means that my coordinates are 1, 5, 1, 5. That is the coordinate vector. In our next question, we let Pn be the set of polynomials of degree at most n, providing a counterexample to show that Pn is not a ring. What we want to show is if I have f times g is not in Pn. I'm going to show it's not closed under multiplication. So we have these two operators. We have addition and we have multiplication. I'm going to show that it's not closed under multiplication. So if I let f equal x squared and g, or n squared, sorry, x to the n, and g equal x. So f of x equals x to the n, g of x equals x, then f g of x equals x to the n times x, which equals x n plus 1. Thus, fg is not in Pn. You could just provide f is x to the n, g is x, or x squared or x cubed. Something of some form in this way. Or you could simply do x to the n, x to the n. As long as n is greater than 1, you're good. Okay. But with these questions, if you feel like you need to provide any extra explanation, please do. There's nothing wrong with providing extra explanation. A5. If we have a linear transformation from V to W, true or false, if the dimension of V equals the dimension of W, then T is a linear operator. And this is false. To be a linear operator, V has to equal W. Just because the dimensions are equal does not mean the vector spaces are equal. If we look at Rn and Pn minus 1 of R, the dimension of these spaces are both n, but this is a set of vectors or n tuples, and this is a set of functions or polynomials. They are related to each other, but they are not, and I repeat, they are not the same thing. Now we move on to A6. And in A6, we're given this representation and we want to look at what it does geometrically. So what we're going to do, or what I like to do, is I like to draw and see what happens to a few points. So if I have the first point here and it's 2, 1, it's going to become -2, -1. So it's going to go here. Okay. Now if I have the point -1, 3, it's going to become 1, -3. Okay. And all of these seem to go through the origin in some way. They seem to reflect through the origin. Okay. But geometrically, we don't reflect through the origin. There's another thing we're doing. What we can see is I can rotate this vector around by What's my angle here? My angle here is pi degree radians. Here, what's my angle? My angle is pi radians. So what's going on here? I have a rotation by pi radians. And what's nice is you don't have to specify if it's clockwise or counterclockwise because it's both. Okay. If f is a linear functional, what can we say about the dimension of v? And where the dimension of v equals n, what can we say about the nullity? Okay. So the big thing here is the dim of v equals n, the dim of w equals 1. The nullity of t plus the rank of t equals n, or the dim of v. But the rank of t is less than or equal to the dimension of w, which equals 1. So because of this, rank is less than or equal to 1. This means that dim v minus rank t is greater than or equal to n minus 1. But we also know that, and this is nullity, the nullity, which equals dim v minus rank, is greater than or equal to 1. We also know that it's less than or equal to the dimension of v, which here in this case is n. So we know that it could be n minus 1 or n. Let v1 and v2 be subspaces of v. Let beta1, beta2, and beta be bases of v1, v2, and v. Can a vector exist in beta1 or beta2 that is not in B? And the trick here is that these are bases, not the span of bases. So the answer is yes. So if we look at the span, if we let beta 1 equal 1, 1, beta 2 be 1 minus 1, and beta be the standard basis, 1, 0, 0, 1. This satisfies if I have the span of 1, 1 being V1, that satisfies it's a subspace. The span of beta 2 being V2, that satisfies it's a subspace of V, and the basis beta, or the standard basis E1, E2, is a basis for V, but this vector is not in beta, and this vector is not in beta. The idea is it's not unique. It'd be in the span of the vectors, but it's not in the set of vectors themselves. 9. Show that cos x is not a linear transformation for the real numbers. There's a bunch of ways we could do this. We could show that the addition of two entries does not have the entries. A whole bunch of things, but I find the easiest is cos of 0 equals 1. Thus, not a linear transformation. Linear transformations preserve the 0. Cos doesn't. It's not a linear transformation. Now here, it's A10, a little bit challenging, mainly because we've never seen it before. What does we mean by f of a? Okay.
And this 3 is involved, which is also kind of confusing. Well, f of A, f of our matrix 2, 1, 1, 3 equals 2, 1, 1, 3 squared minus 3. And now it's 3 of something, okay? And what it's going to be is it's going to be the multiplicative identity for matrices. And the multiplicative identity for matrices, when we matrix multiply, the identity is the identity matrix. 0, 1 on the diagonal, 0 is everywhere else. Well, this equals 2, 1, 1, 3, 2, 1, 1, 3 minus 3, 0, 0, 3. Now, 2 times 1, or 2, 1 times 2, 1 is 5. 2 plus 3 is 5. 2 plus 3 is 5. Now 1 plus 9 is 10. Minus 3, 0, 0, 3, which equals 2, 5, 5, 7. So my answer is 2, 5, 5, 7. Well, there is space for your solution. We want you to put extra work around it so that if there is a simple mistake and we can find a mark to give it to you, we'd like to find that one.